Welcome to the optical communication course. Now, we have seen that earlier that a receiver performance for the receiver performance decision circuitry it will take or it will understand that what about the level of the bit 1 and 0. So we have mentioned earlier for the level 1 and for the level 0 there is some threshold level we have to mention. So at the receiver when we receive the information, that information whether that information will be high level or a zero level. So according to that, we can say that a bit 1 or bit 0 will occur respectively. Now supposed to be we say that higher level, that is 1, if it is a lower level 0. But sometimes what happen when we send a pulse of 1 bit here, means one bit is sent. So in that case, what happen at the receiver? So we are receiving the signal level that is below the threshold. So then receiver will recognize that bit will be a 0 now. Even if we send the 1 bit, but receiver will receive that received bit will be a 0 bit because the level will be a 0. Okay, because level will be below that threshold level. But if you consider that if we send the 0 bit, but at a receiver we are getting the level that will be above that threshold. So then in that case, when we transmit the 0 bit, we are getting that 1. That's why we have seen that probability of transmitting 0 and probability of transmitting 1 that we have seen. So in that case, we mentioned that some particular threshold is there, and according to that, for a given particular threshold, when we have the bit 1 and when we have the bit 0. So according to that, we have mentioned that this is 1, this is the 0, and this particular portion is for the when we send the 0 bit, but we are receiving that 1. And this particular portion is what we can say that when we are sending the 1, we are receiving the 0. And that is nothing but the probability of error that we have seen. And then we have mentioned that some noise is there, and that noise is at the level 1 as well as some noise is at the 0 level. So that noise, we have mentioned that noise variance for the 0 bit sigma 0 and noise variance for the bit 1 that is about a sigma 1 that we have mentioned. And then in between that 0 and 1, this is about a noise variance for 0, noise variance for 1. And this is nothing but what we can say a noise margin for your signal. Within that, information will be there that will be 1 or 0. And if it is above threshold, we can say 1. Below threshold, we can say 0 there. So based on that, we have obtained one particular parameter that is a Q parameter. With respect to level 1 and 0, we say supposed to be 1, I1, and this is about H0, I0. So according to that, we obtain the parameter that is about I1 minus I0 divided by sigma 1 plus sigma 0. So I1 minus I0 is means what? This one is the difference between this particular level I1 and I0. And this sigma 1 and sigma 0, that is nothing but a noise variance for the bit 1 and a bit 0 there. Now we have considered that a noise variance that is sigma 1 means bit 1 is transmitted. So in that case, that noise will be what? A thermal noise plus the noise will be a short noise. So that is about sigma t is a noise variance for the thermal noise. Sigma s is noise variance for the short noise. When there is a 0 bit means what? There is no light. Okay, no light will fall on the detector if there is a 0 bit. So in that case, it has only a thermal noise component. That is about the ideal condition. And we consider that when there is a 1 bit, so then there will be a statistical process. So that's why there will be a short noise. thermal noise is common for both the 1 bit and 0 bit. So that's why here we say that a noise variance for the 0 bit that belongs to a thermal noise only. But in the case of a sigma 1, that is bit 1, so noise variance that will be belongs to the thermal noise as well as the short noise. So now we consider that it's supposed to be that bit is about 1 and 0, we say pulse is transmitted. But in the ideal condition, we're supposed to be considered only that one bit is transmitted. In that case, I1 by sigma 1 plus sigma 0. That's about the U. So according to that, we have obtained that a receiver sensitivity for the detector, and that receiver sensitivity for the detector is 1 by R. That is R is nothing but a responsivity we have considered here. And that is nothing but what? A unity gain responsivity. And Q charge M is about for the detector, F of M. M is multiplicating factor, F of M is figure of merit for this detector. B your bandwidth, we have the Q factor there. 2 sigma T, that is about the thermal noise, Q by M. That is about the receiver sensitivity that we have seen. Now, a sensitivity for the given particular diode, it is depending upon that how many number of electrons and holes pairs are generated. Now, based on that, we say that this one is about a probability of error when we send 1, but we receive 0 when we send 0 when we receive 1. And this one is nothing but what? We say that we are transmitting the bit 1, we receive 1. This one is about a portion we transmit the 0 bit, we are receiving the 0. So from this we obtain that a probability of error, so that is about a bit error we have obtained. So general in the case of a bit error, your system will be a foolproof if that bit error will be of 10 to the power minus 9. That is about the range of the bit error rate is given for the receiver system. Now then we need to talk about that what will be the minimum optical power required for a digital system so that your system will work better, or your system bit error rate performance, how much will the system bit error rate performance will be required for your digital system. So that is nothing but what? The one more term that will come based on this whatever the received signal we are expecting. So according to that, that term is nothing but called as a quantum limit. So quantum limit means what? Generally, a detector detect a signal means what? For a photon, it will generate a electron hole pair. For a given photon, detector will detect the electron hole pair. Now one photon, one electron hole pair. But in the case of avalanche photodiode, that is a multiplicative process. So multiple electron hole pairs are generated. Now consider that here. For one photon, it will generate a one electron hole pair. That is about a process. So we consider that in an ideal condition, that quantum efficiency will be a unity, and it will produces a no dark current. Dark current means what? That is a no electron hole pair is generated in absence of light or in absence of a photon or a pulse. Now in that particular condition, we supposed to be consider that the minimum received optical power required for the specific bit error rate in a digital system. So we're supposed to be consider that a minimum optical power required for the what, for a specific bit error rate in the digital system, and that minimum optical power level what will require for a given particular digital system for a performance of a BER. So that minimum optical power level is nothing but the quantum limit. In another case, what we can say that here we say that a pulse is there, so it will generate a electron and hole pair. So how much is the optical power is required so that it will generate a number of electron and hole pair. So from that number of electron hole pair, so what will be the current is produced, and what will be the, because of this particular current, what will be the received power. So how much will be the received power we required for your given your system, for your given digital system, so that it will work for the specific bit error rate. Now in that case, we consider that the minimum received power level we require, it is depending upon that number of electron hole pair generated in the detector. So we should know that what will be the minimum electron hole pair generated so that it will give the received power. So generally in a system, so you can say that there will be a 21 electron hole pair is to be generated. Then and then that will be the minimum received power level required for your system there. So that is depending upon that a quantum limit, or you can say that it depends quantum efficiency in a ideal case. So we can say that what will be the minimum, that is performance of a BR. So then we need to be consider that if we, our receiver has a zero pulse, means we can say that there are no electron and hole pair are generated. But if supposed to be consider that if we transmit a bit, or if we have a optical pulse, means we can say that is about a 1 bit of information with the interval of a tau here, and then a receiver will reinterpret it, it is supposed to be a zero pulse, because there are, even if because of optical pulse is there, even if it will not generate the electron and hole pair, so then that receiver will interpret at a 0 bit. So then we can say that the probability of electrons, means we can say that n is equal to 0 electrons are excited in a given particular interval of a time. So in that case, what will be the received power? In that case, e raised to minus n bar, and that n is nothing but what, the average number of electron hole pairs. This is nothing but what we can say that average number of electron hole pair. So that's why we can consider that for a given particular received power, what will be the minimum energy is required. So already we say that we have the energy is nothing but what we have considered that HV here, and that is nothing but that energy required for a specific value of a wavelength there. So we consider that in a receiver case, what will be the quantum limit? Quantum limit means what? What will be the minimum optical power required so that your receiver will receive the signal without any distortion or without any noise there. So performance of a system we need to be specified based on this quantum limit there. So that is about in the general case we say that if that BR if it is 10 to the power minus 9, so in that case that system will be a very good system and it doesn't have a noise or a distortion. Now next is about another method for measuring that performance of a receiver, that will be about a eye diagram. So eye diagram is specifying or it is a measurement tool for verifying the a data handling ability of a system. That is about for a given particular bit we transmitting, so whether we are receiving the 0 or 1, and then in what particular period of a time that data is to be retrieved in a digital system. So that is nothing but a eye diagram. So we'll see that we say that we have the bit information that it will be a 1 or bit information will be a 0. So in the presence of we consider there will be a noise and it has some particular duration. So generally a pulse will be likewise. We have the pulse will be likewise. So according to that, this is nothing but what we can say that a eye diagram. This is about your eye diagram. So specific, it looks like that structure looks like a eye. So that's why this is nothing but what we can say a noise variance. And we have the limit here or a performance of a system. So we can measure this one this way here. This is about a level. And according to that, in that particular level, we can say that some particular threshold level is to be mentioned. Above that, we say 1 or a 0 bit. Since we are receiving the information, it has some particular clock. So in that case, the receiver information, if that clock has a clock jitter there for your system, so then there will be a performance degrade, and this is because of a clock jitter. So now that width of the eye is likewise only, and this one is nothing but belongs to that a jitter here. So now we will talk about that what will be happen when we are specifying that particular bit information there. So one generalized eye diagram I am going to draw here, and it is specifying that that bit will be 1 or a 0. So that is a that eye diagram is specifying with respect to that a 1 and 0. That is level 1, and this one is about a level 0. So now we can draw a system. So we have the information if supposed to be a 0 or 1. So there may be a noise in the system. So that's why we are getting that information is likewise. And we supposed to be consider that that system has a 1 or a 0 bit now. Okay, I'll just trying to try to draw this diagram here. Okay, so this one is nothing but what, a zero crossing. We have the zero crossing here, and this particular portion we say that this is called as a eye opening here. Okay, that is about without jitter that we have draw a diagram, but if in this case your diagram will be likewise. Okay, you can consider that this about your diagram. Okay, so likewise that will be your diagram. So in that case, this one is nothing but what we say that eye jitter. When again eye jitter we say here, this is about a eye jitter here. So this is the height of your eye opening here, and this one is about the width of your eye opening. So in that case, width will be likewise. Okay, this one is about the eye width, and here we can say that that information will be what, be off means there is no bit, and be on there is a bit, and with respect to that value is about 80% of that particular period we have to consider, or we supposed to be consider that we need to measure that rise time we supposed to be consider, that will be from 20 to 80%, and in that case that rise time will be likewise. This is about a rise time, that is about a 20 to 80% of this, and similarly we have a fall time we supposed to be consider, this is about a fall time, that is again 80 to 20%. Okay, so this is about the case we supposed to be consider that this one is about it be dark, or we have a dark noise, that's why we can supposed to be consider that about be dark. Now for this given particular eye diagram, so how to obtain the eye diagram on the CRO? On a CRO we have the x and y, we supposed to give the data here, we supposed to give the clock here, and then we can see that the performance of the eye diagram. We'll see that eye diagram on this CRO there directly. So this eye diagram, it is showing that what will be the distortions by at a receiver, and how much will be the allowing time for the data and all. That will be nothing but your, we can say that a eye diagram there. So it is just like a pattern, and that pattern has some upper bound and a lower bound. We can say that upper bound, then it has some particular lower bound for your bit 1 and a 0. We can say that 1 and a 0, that is about a logic level. So that's why you can say B on and a B off here. So now that width of this eye, this is nothing but it can be defined in terms of what, a time interval where we are receiving the signal within that particular period of a time, without any error. So that is about this is about the width of I. So if supposed to be considered from this particular case, this one is nothing but a timing jitter. So this is about the width of this I, and that will be nothing but what we are receiving, or we are receiving the signal in that particular period, or receiving that information of your signal in that particular period of a time. So if that width of the I is a small, that system is not good. So there may be issue of what, there may be issue of a intersymbol interference because adjacent pulse will overlap there. Okay, so that's why we supposed to be consider that a width of I here. And then this one is about the eye opening. If that eye opening is a larger, so then we are getting a sample very easily. Okay, so means sample can be obtained within that particular period of a time because of that eye opening. Eye opening will be a larger. If that height is reduced, so if that eye opening, we can suppose to be consider that height is reduced likewise. So in that case, so there may be a distortion in a data or distortion in whatever the received signal there. So that's why we supposed to be considered to avoid the any distortion. So that eye opening is to be a large is there. So if that eye opening is a smaller, then there will be a large distortion. If that eye is more closer there, or it is to be closer here, then we are not able to identify that a 0 or a 1, or we are not able to distinguish the data information that will be 1 and a 0 there. So that is about, we can say that for a given particular eye, the height of the eye opening in the specific period of a time, so that height of eye opening is nothing but what we can say that a nice margin of your given particular system. This is about a noise margin. And that noise margin, if you calculate that noise margin, it is defined in terms of a what will be the peak voltage for a given particular bit. So supposed to be considered that we have a noise margin for the given particular bit information. Now we supposed to be draw again a one more diagram, so we can easily calculate that or easily obtain that a noise margin. Now we supposed to be consider that a bit information will be a 1 and 0. So what will be the maximum peak level or maximum signal voltage for the bit 1, and what will be the noise margin from the threshold value. This is nothing but a threshold here. We supposed to be say this one is about a threshold. Okay. So now from this we supposed to be say that this one is about your bit information. Okay. This one we supposed to be say that a sampling time for this particular bit here. Okay. Like so this one is about a threshold here, and we have the a noise margin V1 here, and this one is a maximum signal voltage. that is a V2 here. And from this, we supposed to be consider that this one is about a time interval over which signal can be sampled. That is about a sampling time. So within that particular period, from this to this, that is about a time. Within that particular period, we supposed to be measure the data here or receive the data there. That is nothing but a sampling time. So this one is about a base sampling time. Means we can sample from this to this. Okay, from this to this. But this one is about here. This one is about a base sampling time, so that we'll get that exactly information. And this is about a slope. That slope is for a timing error, or that is nothing but a slope that will give the sensitivity to timing errors here. And this one is about a distortion in within a particular period of a time. Distortion at zero crossing. Now we can find out a noise margin. It is in percentage here. So V1 by V2 into 100 will get that percentage in terms of percentage. Okay, so that is about your value. So that is about, we say that a ratio of the peak signal voltage V1 for a given particular bit sequence to the maximum signal voltage V2, and that is measured in terms of what we can say a noise margin. And for a given particular eye, so this is about a eye opening, and this is about the width. So that is about the whichever the eye opening is there. If supposed to be that eye opening is varying, so in that case we can supposed to be get that there will be a more distortion. And if supposed to be through this supposed to be eye is closes, this particular period is varying here. So in that case, so there may be a timing error. And if supposed to, why this timing errors occur, because that slope is reduced. Okay, we can say that this one is the slope instead of that this one. That's why it will be closed. That's why that because of that slope, that slope will give that a sensitivity with respect to particular time. So this one, if that eye closes, when we have that variation in that particular sampling time, so then there will be a possibility of a timing error, and that timing errors are increased. So because of that, slope will be decreased here. So according to that, we'll get that there will be a probability of a timing error there, and that it jitter we supposed to say here in the optical fiber, because of we supposed to be consider that the clock pulse, there may be a variation in the clock. Okay, that is about a pulse. In that case, that particular variation in the timing pulse, that is called as a timing jitter. So that timing jitter in a system, that will be arises from the noise at the receiver, and that noise at the receiver because of that pulse distortion in the optical fiber there. So according to that, we can find out for the given particular a distortion, and we are specifying the a bit interval for the 1 and 0. So in that case, so timing jitter we can calculate. That is again in terms of percentage. That is del t is nothing but a duration. That is a amount of distortion in the particular sample timing interval there. With respect to that, one bit of a duration is transmitted into 100. That is, you will get that in terms of a percentage there. So that we supposed to be considered here. That is a distortion at a zero crossing, and that distortion is nothing but a delta t. Okay, this is nothing but a delta t. There is about a distortion at a zero cross. So similarly, we can calculate that for a given particular I diagram, what will be the a rise time. Generally, we say that a rise time is about what a timing duration from a 10 to 90%. So generally, we need to convert from a 20 to 80% there to a 10 to 9% of this rise time there. Generally, this rise time it is a interval between the point where the rising edge of the signal reaches the 10% of its amplitude to the time where it reaches to the 90% of its final amplitude. So that is we supposed to be consider that the rise time it is about a 20 to 80% from the 20% of amplitude to the 80% of amplitude. But here we consider supposed to be 10% of its amplitude to the 90% of its amplitude there. That's why we need to convert from that 20 to 80% of a rise time to a 10 to 90% of a rise time. So then we will get that 1.25 into t of 20 to 80%. And that will give us the a rise time. So now in general, if you consider that a eye diagram, typical eye diagram will have the information of a zero line. Now like this is about a zero. So this is about a zero bit now. And then we supposed to be consider that this is about a one now. So this one is nothing but a portion of an eye for a bit one and bit. So this way you will see that eye diagram in a system. So typically eye diagram we supposed to be see, and this particular portion we supposed to be consider this about a jitter, and for the given particular system, and this is nothing but a eye opening, and from this to this we supposed to be consider that is about the width of the eye here. So from the eye diagram we supposed to say that what will be the BR required for the given particular system. So typically for a given particular system, ideal case in ideal or in generalized case, we supposed to be say that the eye opening is a large, so there won't be any amplitude distortion. If eye width is a large, there won't be any timing distortion. So that your system will work better for a given particular a BR. So generally one system if we have consider that, so we supposed to be say that a BR requirement and what will be the Q factor requirement, Q quantity of a Q. That quantity of a Q supposed to be say that I1 minus I0 by sigma 1. So that BR and Q factor that both the factors that causes the errors in the digital system. So we consider that what will be the BR performance and what will be the Q factor there for your digital system. So that is about your a eye diagram and a receiver performance, and we have seen that for a given particular system, so what will be the receiving information, what will be the receiving data we require in the digital system. Now supposed to be, if we consider that your system is not supposed to be a analog one, or it is supposed to be a analog receiver, so in that case what will be the a signal to noise ratio. So for that purpose we should supposed to be know that what will be the a total noise in the given particular system. And the total noise is nothing but what, a twice q plus ip id m square f of m, that is ip is nothing but a primary photocurrent, d is nothing but what, a dark current we have. This one is about a receiver, b is receiver, plus twice of q il ve, that is a surface leakage current here, plus 4 kb t ve by equivalent resistors of this, equivalent load resistors for this receiver there into ft. That is about a noise figure of this baseband amplifier. That is about, we can say, a noise current, and a source current for the receiver, it will be what, 1 by 2. Then we have the detector responsivity, that is about r m m, that is about a photo detector gain here we supposed to be considered, m is a photo detector gain, and this small m is for the modulation index for the signal into a BR bracket. That is about a received power. So we can calculate that a received power, or we can write directly, that is about a signal to noise ratio. Approximately we supposed to be consider that is by IN, and after solving, just I am writing directly here is by IN, that ratio. So that will be is equal to what, 1 by 2 m square responsivity care r square 4 kb t beta e by equivalent resistors and a t. So this one is about a signal to noise ratio. If we supposed to be consider that your system will be receiving the data, or that is about a analog receiver, and that analog receiver we supposed to be consider that what will be the signal to noise. So that is about a receiver performance that we have seen. Okay, and we supposed to be know that what will be the probability of bit 0 and probability of bit 1. We supposed to know that what will be the quantum limit, what will be the what will be the received power level required, and that minimum received power level required is depending upon that number of electron hole pair generated. Probability, that is nothing but a 21 electron and hole pair are required for a given particular system, so that it will receive some bit, some information there. That's all from this optical receiver performance.